There are two kinds of statistic, the kind that you look up and the kind that you make up. Aren't statistics wonderful things? At their best, they can communicate genuine truths about the wider world. A good set of statistics can help you plan an economy, analyze social issues, and let you know the key factors that influence your life. Good statisticians are rare and can be nation-changing. But imagine for a second that you are not the honest, decent fellow that I am sure you are. Let's say that you don't want to use statistics to help people understand reality, but instead to persuade them of a particular point of view. You want to manipulate the public to follow your party or buy your products or take a particular stance on any of the key issues of the day. In this case, you're going to have to learn a very different skill. You will have to carefully misuse statistics to guide people's minds to your point of view, all while hiding your dishonesty. And this is just what we shall look at today. Get ready to learn how averages mean very little, what statisticians and artists have in common, and so much more. Now, you may have ethical qualms in learning about these techniques, and I totally understand where you're coming from. However, the fact remains that every single one of the strategies that I'm going to talk about today is currently in use by political organizations, corporations, and even governments. And this happens all around the world. But once we know these dastardly techniques, we are that bit more prepared to fight against them. I also want to clarify that I'm not going to say anything particularly original in this video. Everything that I'm going to talk about has been said by professional statisticians many, many times. The two main sources that I will draw upon are How to Lie with Statistics by Daryl Huff and Flaws and Fallacies in Statistical Thinking by Stephen Kent. And I highly recommend that you read both. They are phenomenal books. I should also mention that I am not a professional statistician, and if I've made any mistakes, as always, they will be in the pinned comment below. But first, let's look into perhaps the most basic statistical manipulation tactic, but one that is surprisingly common. 1. Devious definitions. If I told you that 90% of dogs have violent tendencies, how would you interpret that? Almost certainly the first image that comes to mind is of a huge hulking hound mercilessly mauling someone in the street. And if this is what you picture, then that statistic becomes really quite scary. You might become terrified of dogs and even argue that their breeding should be limited or they should be banned entirely. After all, 9 times out of 10, when you see a dog, they are just a violent killer lying in wait. If you just glanced at that statistic, you would become more fearful, more angry, and very likely more anti-dog. But hang on a second, what does violent tendencies actually mean here? In common parlance, it signifies a few things: aggression, biting, growling, and doing all of this on a semi-regular basis. But what if, in my hypothetical study, I did not define violent tendencies in this way? Instead, I defined it as any sort of biting behavior from puppyhood to the present day. In this case, I would include not only dogs that have chomped down on the innocent passers-by of Britain, but also those that harmlessly nipped people when they were very little, even if this resulted in no injury. If you have owned a dog, then you will know that this will include almost any dog, as most of them go through a nibbling stage when they're very young. This definition would make the 90% statistic a lot more understandable, but it also takes the bite out of the claim, if you'll pardon the pun. No one is going to be worried at the idea that dogs might nibble people when they are very small puppies. We already expect it. But by widening my definition of violent tendencies to include this ordinary behavior, I can whip up a scare story about some perfectly sweet canines without having to outright lie at all. If you dug through my hypothetical paper, no doubt you would find this definition stated explicitly somewhere. But this is also very unlikely to be how the finding is reported. The headline, "Dogs are violent killers," would be on the press before someone even had time to skim the introduction. And this example demonstrates just how important it is to check the definitions a statistical claim is using. For instance, the word poverty has vastly different definitions based on which study or report you are reading, and this can make it very difficult to compare findings from paper to paper. Terms like antisocial behavior or well-being can mean wildly different things in different contexts. And without checking to see how this particular author is using the term, the statistics in question can obscure the truth rather than illuminating it. Of course, if you want to deceive as many people as possible, then you can use this definitional wriggle room to your advantage. Additionally, failing to properly clarify your definitions is perfect for facilitating our next trick. If you want to help me make more videos like this, then please consider subscribing to either my channel or my Patreon. The links are in the description. 2. Strange inferences. Almost everyone agrees that human height is normally distributed within a sex category. That is, a plurality of men are around average height, and then slightly less than that are a bit smaller or a bit taller than average, and a tiny fraction of men are much taller or much smaller than average. This could be represented on a graph like so. If you just ask men what their height is, then you get a slightly different story. This graph is from a CDC report where they asked men the question, how tall are you without shoes on? As you can see, it is very nearly the normal distribution we would expect. But something strange happens around the height 5'11". Here, there is a strange dip in the number of men at this height, and there is a sudden rise in the number of men who are 6 foot tall instead. This makes the data appear strange. How could it be that the heights of men are almost normally distributed, apart from this strange cluster around the 6 foot mark? If we inferred from this graph that male height was truly like this, then we could tie ourselves in knots attempting to explain it. Perhaps there is some evolutionary reason why men are more likely to be 6 foot tall than 5'11" in the US. Maybe there is a secret gene which makes men skip over being just under 6 foot and propels them forward to the real thing. Of course, the likely explanation is a lot less dramatic. A lot of men want to be taller and are known to lie about their height to the tune of around half an inch. Additionally, being considered over 6 foot comes with increased perceived attractiveness, and then many people would consider you as tall. Thus, a lot of men who are 5'11", but really could probably get away with saying they are 6 foot, will say that they are in fact 6 foot because of these social pressures. This is quite a light-hearted example, but it illustrates something really important. Sometimes it seems like we can infer a certain conclusion from a statistic, but in fact, any such attempt would be misleading. In this case, we have to bear in mind that our original statistics were about reported height and not just about height. So we cannot straightforwardly infer from one to the other without considering what confounding factors might have got in the way. Of course, if you want to mislead people, then you can make use of these faulty inferences to great effect. Let's imagine that you wanted to convince me that a certain breed of dog, say Cocker Spaniels, is profoundly dangerous. So you conduct a study, and lo and behold, it is shown that the vast majority of your sampled Spaniels are violent, aggressive, and bite people regularly. I am shocked and go home in confusion, considering what to do about these vicious creatures. However, I have been misled, because it turns out that when you collected your data, you did not study your average Cocker Spaniel. Instead, you took a sample of Cocker Spaniels who were being taught to control their aggression at a dog trainer's. Here, you would have taken a statistic about one group, Spaniels undergoing aggression training, and applied it to another group, all Spaniels, without telling me. This is a classic faulty inference, but it could easily be used to manipulate me. And the particular strategy of this example ties in nicely with our next point, where we look into the murky business of sampling. 3. Samples and representativeness. When a statistician or a researcher is collecting their data, they are very rarely studying the entire population they are interested in. And this makes a lot of sense. Imagine if every time we wanted to figure out if the cost of living had increased, we needed to collect the price of every single product and service in the country. It would take forever, and by the time we'd finished, the prices would have changed anyway. Thus, researchers tend to collect a sample from their target population, in the hopes that this will represent the whole population to a certain extent, and thus allow them to make inferences about it. However, at this stage, a whole manner of things can go wrong, either intentionally or unintentionally, that can create misleading data. One is just by having a sample size that is too small. If I wanted to make some statistical claim about an entire gender, I would need a massive sample. Human beings have so much variability that if I wanted to say something about basically half of them, I would need a very large dataset to draw from. However, if I just wanted to convince people of a particular conclusion, then I might instead take a relatively small sample and then stretch those results beyond their reasonable limits. So I might interview 15 men about what they want out of life. Then, if 10 of them answer that making money is their top priority, I can, without strictly lying, say that I found that 66% of men say making money is their #1 goal in life. If I just present this figure without mentioning the sample size, then it sounds incredibly dramatic. But if I reveal that my survey was only on 15 men, then the hasty generalization is immediately revealed. An example of this from How to Lie with Statistics was the claim that 1/3 of women who attend college marry a staff member. It turns out that this particular survey was conducted in the early days of women having access to higher education in the United States. There were 3 women in the year sampled, and one of them ended up marrying a staff member. I'm sure you don't need me to tell you that this was a bit of a dodgy move. The appropriate sample size is going to depend on a myriad of factors, including how much internal variance there is within your target population. I might only need to take a handful of cells from your body to make a claim about the structure of the DNA in most of the other cells, because the structure of DNA remains relatively uniform throughout your cells, or so I'm told. But if I wanted to say something about all companies, then that would require a far larger sample, because there is such a huge difference between running an international airport and managing a publishing business. Another misleading way of sampling is to take a deliberately misrepresentative sample and then generalize that beyond its means. This is essentially what we did in the previous section, where we took a sample from Cocker Spaniels with rage issues and used that to make claims about all Cocker Spaniels. However, this is not always so blatant or deliberate. Famously, some studies in psychology have impressively large samples, but a disproportionate number of people in those samples are university students living in the United States. This is not malice, it is a natural result of the fact that the most convenient group to use in experiments for professors working at American psychology departments are students. But, as many have pointed out, it does limit the generalizability of their findings. And funnily enough, we have our own casual version of this biased sampling for our everyday non-statistical judgments about the world as well. For instance, let's say I wanted to make some general statement about humans as a whole from my personal experience, as you often see people do. Well, what I'm doing is making a loose judgment based on the data set I have at my disposal, which is the evidence I've gathered from my experience interacting with people. However, this is not necessarily a representative sample of humanity. The overwhelming majority of people I've interacted with have been from the UK. I know a disproportionate number of philosophy students, and a plurality of my interactions are taken up with a small group of my closest friends and my close family. So I would have to be extremely careful about the sorts of general conclusions I can draw from my experiences. This is probably why you hear me use the phrase "some people" quite a lot in my videos. I'm trying to acknowledge the limitation in my dataset. Of course, if you do have a general finding, then that is often communicated through the use of averages. But this comes with its own trials and tribulations, because the phrase "on average" can conceal a multitude of sins, as we shall soon find out. 4. The average Joe. According to what I can find from the Office of National Statistics, in 2010, the average man in the UK was 5'10", about 83 kilos, and wore size 9 shoes. He had around 2 children, was 38, got married at 30, and will possibly remarry at 46. These figures are often found by taking an average of each individual property, age, height, income, etc., and then collating them together into a loosely defined average Joe as a sort of rhetorical device. There is nothing inherently wrong with this. It is a fantastic way to communicate a large amount of data very quickly. However, it is easy to get the impression that most people you meet are going to have all of these properties, but that is far from the case. Very few people are average in all areas of life, and so paradoxically, the average person very rarely exists in high frequencies. In some ways, they can't exist. No one can have 1.96 children. This is the first of many false impressions an average can give, and considering how often averages are used in news articles, opinion pieces, and more, it is important to clear up some of these potential confusions. Firstly, there are many different types of mathematical average. So many that I could not possibly go through all of them in this video. But the most basic examples of averages are the mean, the median, and the mode. But these can differ wildly within the same dataset. Let's use an example to illustrate. Say we have a set of 5 people, and their yearly incomes were £5,000, £5,000, £15,000, £20,000, and £500,000. If we wanted to find the median income, we would order them by size and then pick out the middle value. Since this is a set of 5, we would pick out the third value, which would be £15,000. The mode is just the most common value in the set, so that would be £5,000, since we have 2 instances of people earning £5,000. And only 1 instance of any other value. Finally, the mean is the sum of all the values divided by the number of values. So we would do 5,000 plus 5,000 plus 15,000 plus 20,000 plus 500,000 and then divide that figure by 5. So the mean income would be £109,000. Now, Which of these is the true average? Well, in a sense, they all are. These are all perfectly mathematically legitimate averages. But by themselves, they can each be misleading. For instance, if we just presented the mode, then we would think that our set only consisted of people on low incomes. If we just showed the median, we would think that the set contains slightly richer people, but on the whole still relatively impoverished. However, if I told you that the average income amongst these 5 people was £109,000, then you would think this was an immensely rich area. None of these figures give the full story. And importantly, when someone says an average, they could mean any one of them. Part of the trouble is just taking an average does not tell us what the spread of the data is. That is, how varied our figures are. Imagine that I was a government official looking to see which areas of the country needed additional funding due to low average income. If I was just presented with the mean income, I would probably skip over this area entirely because it is so absurdly high. But then I would be ignoring the fact that almost everyone in the set is earning below the full-time minimum wage for the UK. There are many ways that statisticians communicate the spread of data points. They might tell you the standard deviation or the variance, but we don't necessarily need to get into these technicalities. The important point is to have a healthy skepticism when averages are presented to you by themselves, as if they alone, with no other information, reveal some profound discovery. It is true that the more normally the data is distributed, the more likely it is that the median, mean, and mode will resemble one another. But if we don't already know this, then we can be easily misled by a shocking average that obscures the nuances of the data. This can come out starkest in what are called bimodal distributions. Here, the data points are clustered around 2 peaks with a dip in the middle. For such distributions, the mean and median will likely fall into the middle trough. Honestly, if there is one takeaway from this video, I really hope it's this. Be careful of averages. If they are presented without any additional information, such as the variance of the data or its distribution, they can be unhelpful, or at worst, deeply misleading. But next, we will look at an incredibly common mistake in statistical reasoning, and one that a surprising number of us make. 5. The Buttery Biscuit base rate neglect. If I could put you in a room with either your romantic partner or a total stranger, who would you feel safer with? The answer seems obvious, your romantic partner, right? But the fact is, you are much more likely to be killed by your romantic partner than by a stranger. That's a true fact, you can look it up. And this goes for almost any unpleasant thing that can happen to you. Be it emotional trauma, sexual abuse, or assault, these are all more likely to be committed by someone close to you than by a stranger. But can you spot the mistake that I've made here? I am ignoring 2 really obvious facts. 1, you have to have an interaction with someone in order for them to murder you. And 2, you interact with people close to you far more than any given stranger. So while it might be true that someone close to you is more likely to murder you than someone you've never met, it doesn't follow that you are safer with someone you've never met than with someone close to you. There are a couple of reasoning errors going on here, but one of them is called base rate neglect. And once you see it, you start to find it everywhere. There are more people dying from car accidents now than there were 100 years ago. Does this mean that cars have become less safe? Obviously not. It is that both the number of people and the number of cars have grown considerably since 1924. And this becomes even more interesting if we introduce the idea of a hypothetical test. For instance, let's say that I had a device that could detect with 99% accuracy whether someone was a serial killer. So it would only give a false positive 1 out of every 100 times it is used. What an amazing device, you might think. This will save many lives. But the truth is, it is next to useless. This is because the base rate of serial killers in a population is so astronomically low that the false positives would be through the roof. If the machine told us that someone was a serial killer, we would still have to concede that they are almost certainly not a serial killer. However, if you just hear 99% accurate, then it's very easy to think that almost everyone the machine beeps at is a cold-blooded murderer. To repurpose an example from Daniel Kahneman, imagine I described someone as wearing glasses, an avid reader, and an amateur poet. Then I asked you to guess whether they were a librarian or a farmer. Kahneman found that many people would, probably incorrectly, guess that they were very likely to be a librarian. This is because the description more accurately fits the stereotype we have of a librarian. But there's a good chance that the person in question was a farmer just because there are far more farmers than librarians, to such a degree that a great many properties that would occur at higher rates among librarians will still find more gross instances among farmers. Another dramatic and illustrative example is as follows. In 2023, 10 people were killed by sharks, and 12,000 people die each year from falling down the stairs. Does this mean that swimming in the open sea with sharks is less dangerous than climbing the stairs? Clearly, the answer is no. Very few people will ever encounter sharks outside of aquariums, whereas millions upon millions of people walk up and down stairs every single day. The number of shark interactions amongst the general population is so low that the figure of people attacked is also going to be low. This is not to say that sharks are especially dangerous, just probably more dangerous than not taking the lift. And believe it or not, shark attacks are a fantastic segue into our next topic. 6. The abuse of proportions. The UK newspaper The Guardian recently ran the following startling headline. Global shark bite deaths doubled in 2023, with 40% occurring in Australia. Well, goodness gracious me, that does sound worrying. Twice as many people died from shark attacks last year than in 2022. We ought to sound the alarm. Wake up the aquatic police. Something must be done about these rampant predators. However, if you're already on the ball, then you might suspect that something fishy is afoot. I'll see myself out. The terror that one should reasonably feel at shark attacks doubling in a year entirely depends on what the figure was the previous year. If it was several thousand, then yeah, that's pretty worrying. But the actual 2022 figure for shark attack deaths was 5. And thus, as we said in the previous section, the 2023 figure is 10. It's not exactly cause for alarm, is it? And this reflects a whole host of ways that proportion and percentages can be twisted to put your own personal spin on reality. For instance, let's say that I'm running a business and my profit margins are 0.5%. However, the following year, I managed to increase them to 1%. We can present this figure in a lot of different ways to minimize or maximize the achievement. I could say that profit margins have increased by 0.5 percentage points, or I can say that they have increased by 100%, or that they are 200% of what they were last year. Obviously, whether the increase is actually laudable or unremarkable or disappointing is going to depend on what industry you are in and what your competitors are doing. But undeniably, saying my profit margins are 200% of what they were last year sounds a hell of a lot more impressive than my profit margins went up 0.5%. And both are absolutely true, but they leave a very different impact on the reader. If, like me, you know a vanishingly small amount about most industries, then you are likely to be very impressed by the 200% figure and much less impressed by the 0.5% figure. Essentially, a proportion or percentage does not tell you all that much if you don't know the base figure it's working from. If I say that cancer deaths are up 10%, then that is a really big deal because cancer deaths are already a very large set, about 10 million a year. But if I say that the number of people who have choked to death on goldfish while trying to swallow them whole after stumbling in from a night out horrendously drunk has increased by 300%, then that might just mean that 4 people have done it this year compared with 1 last year. We can also gerrymander percentages by being very selective in how we categorize our datasets. For instance, if I published a book on comparing the philosophies of Nietzsche and Dostoevsky, and I say that it's taken up 50% of the market share in its genre, what does that tell you? It entirely depends on what I'm referring to when I say genre. If I mean it has 50% of the market share in philosophy books, then that would be insanely impressive. If the category is existential philosophy, that would still be incredibly impressive. If it was books comparing the philosophies of Nietzsche and Dostoevsky, then it would be quite a bit less impressive. And if I meant books comparing the philosophies of Nietzsche and Dostoevsky written by people called Joe who run YouTube channels, then frankly, it is disappointing that I've not completely cornered the market. This is just one of the reasons why so many people can truthfully claim they have a best-selling book. So, be wary of percentages and proportions. They can be a wonderfully informative way of examining data, but if you don't have all of the relevant information, they can also obscure, twist, and spin claims to make them look much more or less significant than they actually are. But now we shall move on to one of the most famous forms of statistical fallacy. We will have all heard this phrase hundreds of times, but I think it's worth stopping to consider it in detail. 7. Correlation and causation. Correlation does not equal causation. This is an easy thing to say, and many of us do believe it, but it's worth unpacking exactly what this phrase means, and what its implications are. How do correlations arise, and what makes some claims to causation very strong, and others incredibly spurious? Obviously, this is a huge topic, and I cannot hope to do it justice in this video, but let's scratch the surface just a little, so we can be slightly better casual statisticians. So, first of all, while correlation does not always equal causation, causation does often, but not always, give rise to correlations. For instance, the number of times I knock a glass off my desk will correlate very strongly with the number of times that I find smashed glass on my floor. And philosophical worries aside, there is a very clear causal connection between the two. But correlations are not always so clear. For instance, I am loosely part of the atheist community online, and I have seen some people point out that countries with higher rates of atheism also have a tendency to have lower crime rates. Often the Scandinavian countries are used as examples of this. Now, this correlation may hold, I haven't looked into it fully, but it's also worth noting that the wealthier a country is, the more likely it is to have both higher rates of atheism and lower rates of crime. So the situation isn't as simple as atheism causes low crime rates. It could turn out that atheism is a causal factor, but that would require further argumentation. We have an alternative plausible hypothesis that the increase in prosperity is a causal factor both in the rise of atheism and in the lowering of crime rates. If this is true, it is an example of X and Y being correlated because there is some further factor, Z, which is causing both of them. Again, I'm not trying to give a definitive judgment on this particular claim. It's just a nice example of two competing hypotheses. It can also happen that X and Y are correlated not because X causes Y, but because Y causes X. To return to my example of the correlation between dropping my glass on the floor and there being broken glass on my floor, it would be bizarre for me to claim that the glass on the floor is causing me to knock my glass off the table. Mere correlation does not tell us which direction a causal chain would run, if any, and we would need to do further investigation to uncover this. Judea Pearl argues this should be done through an interventionist experiment. That is, we keep the other factors as stable as possible, change the purported causal factor, and see what happens. However, such interventions are not always available to us, and we may need to formulate multiple hypotheses concerning causal relationships, and evaluate each for plausibility based on background information, future observation, and so on. This is a complicated topic, and it's not one I'm massively qualified to talk about, but I've left some links to articles in the description, which go into this topic in more detail. Additionally, sometimes there are correlations that just emerge by chance. Tyler Vigen has a wonderful website dedicated to just this. He has recorded correlations between cat memes and cars being recalled for airbag failure, the number of phlebotomists in the US and arson attacks, and a correlation between bachelor's degrees awarded for library science and Google searches for how to hide a body. Clearly, there is unlikely to be a causal story involving these correlations, and yet they remain statistically observable. So sometimes correlation is just that, and only that. And finally, there is the assumption that just because one thing followed another, that thing was caused by it. Obviously, sometimes this is true, as in the case of my glass. But the trouble is when this is generalized into a rule. For instance, the American Declaration of Independence occurred just a month before the death of Scottish philosopher David Hume. If I was feeling particularly dramatic, I could craft a tale of how the empiricist was so heartbroken at the conflict in the States that he lost the will to go on. This might lend it some emotional resonance, but it wouldn't make it true or plausible. This is sometimes known as the post hoc ergo propter hoc fallacy, which is just Latin for after this, therefore because of this. But assuming causation is not the only way that statistics can be misrepresented in the causal realm. Even when there is a genuine established causal chain, that still leaves wiggle room for manipulation, as we shall soon see. 8. Causation and attribution errors. We live in a complicated world, and often the causal relationships between events, trends, and objects are no less complicated. But if we want to engage in some selective interpretations, it is very easy to twist the facts to suit a convenient narrative. And this is particularly common when assigning responsibility. For instance, imagine you are standing for a national election, and you want to make it clear that the person who held the office for the past 5 years is an absolute buffoon when it comes to economics, incapable of even the most basic informed decision-making. And you have the facts at your fingertips. In the last year of their office, economic growth slowed down considerably. There was a huge swathe of job losses. The number of businesses closing shot up dramatically, and homelessness reached a 10-year high. It might seem that you have a really strong argument for the incompetence of your opponent, but let's pull back the curtain and reveal that this election is taking place in late 2009, just after a financial crash that shook the economic foundations of the entire world. Would it be strictly fair to pin all of this economic disaster on your opponent? Probably not. But what politician would pass up the opportunity for such a crackingly persuasive spin? Of course, this is not to say that leaders are never responsible for the economic and social conditions of their nations. It is just that the causal relationships here are obviously very complicated, and a simple presentation of bare statistics, as above, cannot tell the whole story. On the flip side, someone can try to evade responsibility by over-attributing causal relevance to outside factors, when in fact they were in the driver's seat. They might try to obscure the causal role of their own decision-making by pointing to carefully chosen statistics that show their mistakes as part of a general trend. If there is a general trend in this video, it is that things are often more complicated than they appear. One thing to bear in mind here is that some psychologists have hypothesized that we have a tendency to over-attribute causal relevance to people's choices and dispositions, while under-attributing it to external factors. This is often known as the fundamental attribution error. According to this hypothesis, if we are told that someone has lost their job, we are prone to overestimating the relevance of their effectiveness as an employee and underestimating the relevance of other information, such as general trends in the state of the economy. I should also mention that the generality of this hypothesis has itself been challenged. So I wouldn't be too hasty in accepting it as a rule, I just thought it was an interesting example. But finally, let's move on to what many statistical ploys boil down to. And it is a truly pernicious argumentative move. 9. The dazzle of statistics. The great allure of statistics is often in their perceived incorruptible objectivity. No one can question the statistics. They are just there, standing apart from our petty human affairs like platonic gods. And in a lot of cases, this is true. The statistics themselves have not done anything wrong, they are just numbers and they cannot bear moral properties. But amongst all the exemplary mathematics and ethically pure formulae, there are messy, imperfect human beings involved. In the causal chain that stretches from the world as it exists to a statistic appearing in a newspaper or an advert, there are researchers, analysts, interpreters, journalists, editors, advertising executives, and more. Any one of these people can, intentionally or not, interfere with the presentation of these statistics to spin a particular message. They might include extreme outliers and make it look like the average income in a given area has shot through the roof, when in fact the majority of incomes have remained stagnant or even slightly declined, as reflected by the median. They might assume a causal relationship where none exists, or over-attribute responsibility to one causal factor among many. They might present a small change in figures as a huge change in percentage, provided the original base was small. They might not tell you that their survey or study was only conducted on a tiny sample or a very skewed sample. They might infer from results about one population to a subtly different population without letting you know. And all of this can be done not out of malice, but simply a lack of familiarity with what can and cannot be inferred from particular statistical information, and what is left out when you exclude certain things. The danger emerges when we fail to recognize this and begin to treat statistics, any statistics, as if they fell from heaven and that they are totally immune to distortion or misrepresentation. Then we can become suckers, ready to be manipulated by bad actors who are more interested in capturing our minds than representing the full breadth and limitations of their claims. But the flip side is also treacherous. Just because statistics can be manipulated does not mean that they all are. Just as rhetoric can be used to make poor arguments appear strong, and a confident delivery can make even the strangest of claims seem temporarily plausible, statistical manipulation can obscure the truth. But just like we don't decide speeches are always misleading just because lies exist, it would be a mistake to think that statistics cannot tell us anything about the world. Thank you to Daryl Huff for that particular comparison. But I hope this video has convinced you to look at statistical claims with a healthy skepticism, and to put a little bit of time into investigating how these figures were found, and how they are being presented, before you believe them wholeheartedly. Like so many aspects of life, there is no simple algorithm for saying exactly when a statistic or a presentation of a statistic is good or bad. But with this information and a bit of practice, hopefully we can all learn to become connoisseurs of statistics, rather than blind believers or outright cynics. And if you want to learn more about reasoning mistakes and manipulative strategies, click here to watch me examine Schopenhauer's famous essay on how people fool you with rhetoric. And stick around for more on thinking to improve your life.